Hey there, it's Shannon MATHCHICK Myers, and today we're going to check out the ratio and root test. So here we go, the ratio test. Let the summation a sub n be a series with non-zero terms. So a lot less about the conditions on these, which is nice. The series summation a sub n converges absolutely, another nice thing, when the limit as n approaches infinity of the absolute value of the ratio of the n plus first term to the nth term of that sequence is less than 1. Now the series summation a sub n diverges when that limit as n approaches infinity of the ratio, absolute value of the ratio of the n plus first term to the nth term is greater than 1, or when this limit goes to infinity. The ratio test, unfortunately, is inconclusive when this limit is exactly equal to 1 as n approaches infinity. Okay, so let's check out how it works with the ratio test. So determine the convergence or divergence of the series using the ratio test. So here, is this the easiest test to use? Honestly, no. I would use the geometric series, but it's a nice way to practice the ratio test. And besides, we can figure out if it's got absolute convergence as opposed to just convergence on the ratio test. So let's check it out. We'll still write our steps down. So step 1, you name the test. And we're using the ratio test. Step 2, check our conditions. And for the ratio test, real easy. It just has to be a series. Sorry, I'll do the specific series. This series has to have non-zero terms. So 2 over e, that's a little bit less than 1, raised to the nth power has non-zero terms. And that's all we need. And third, we will run the test. So we will have the limit as n approaches infinity of the absolute value of, now these can get a little bit, ugly to write, so I'm going to write them like this. 2 over e to the n plus first term divided by 2 over e to the nth term. Actually, this one won't be so bad. It's in absolute value, but 2 over e is always positive. So we can take that absolute value off and simplify, because if we have the same base of 2 over e, so you just subtract the exponents. So n plus 1 minus n is just 1 for our exponent. So we'll get the limit as n approaches infinity of 2 over e raised to the 1. Now e is 2 point something, so I don't know what that is, but it's going to be less than 1. And so our conclusion will be the summation as n goes from 0 to infinity of 2 over e to the n converges absolutely by the ratio test. And we're done. Cool, cool? All right, excellent. So next one, part B, a little more complicated, right? So again, we'll start off by naming our test. We'll use our ratio test. And step 2, conditions. Only condition is that the summation as n goes from 0 to infinity of 2 to the n over n factorial has non-zero terms. And that is true. Remember, 0 factorial is 1. We'll put a little check. And step 3, run the test. And so now I'm going to write this just a little bit differently. We will have the limit as n approaches infinity of the absolute value of 2 to the n plus 1 over n plus 1 factorial. That's the n plus first term. And then it's going to be divided by the nth term, which is 2 to the n over n factorial in absolute value. Now, we have a positive term series, so we don't need the absolute value. And remember, when you divide by a fraction, you invert and multiply. So we'll end up with 2 to the n plus, we need our limit notation. The limit as n approaches infinity of 2 raised to the n plus 1 over, I'm going to write this as n plus 1 times n factorial, because I know that we're going to have an n factorial that we're dividing out, and then we'll have our 2 to the n. So the n factorials divide out to be 1, and remember that 2 to the n plus 1 divided by 2 to the n, when we subtract n from n plus 1, we'll just be left with 2. So we'll have the limit as n approaches infinity of 2 over n plus 1. Well, this limit is equal to 0, which is less than 1. And so our conclusion is that the summation as n goes from 0 to infinity of 2 to the n over n factorial converges absolutely by the ratio test. Cool, cool? All right, next up, we have an alternating series. So the nice thing about using the ratio test is that the negatives will all go away in that absolute value. So step 1, we have our test. Again, we're using the ratio test. Fingers crossed that it works. And step 2, conditions. The summation as n goes from 1 to infinity of negative 1 to the n plus 1 times quantity n plus 2 over n times n plus 1 is a series with non-zero terms. So we're good on that. And then running our test. So we'll have the limit as n approaches infinity of absolute value. The negatives are going to go away, so I'm not even going to include them. And then we will have n plus 1 plus 2 over n plus 1 times n plus 1 plus 1. That's our n plus first term. And then we're going to multiply by the reciprocal of the nth term. So we'll have n times n plus 1 over n plus 2. And again, the absolute value takes all the negatives away, which is great. So this will be equal to the limit as n approaches infinity of. So let's see what we end up with. We will simplify this. We'll have n plus 3 over n plus 1 times n plus 2 times n plus 1 over n plus 2. The n plus 1s divide out. And what's going to happen is that this is going to end up equaling 1. But I'll show you the work on it. If we expand out, we'll have n squared plus 3n over n plus 2, the quantity squared, which will be n squared plus 4n plus 4. And then if you multiply each of them by 1 over n squared, which is the highest power in the denominator of the denominator expression, then we will get the limit as n approaches infinity of 1 plus 3 over n over, sorry, this should be an n squared, my bad, over 1 plus 4 over n plus 4 over n squared, which is equal to 1. So that means the ratio test is inconclusive. So we have to run another test. So here we go. We'll take attempt number 2 here. I know it's a bummer. Step 1, test. Well, for this one, a good one to use would be the alternating series test. Step 2, conditions. So for the alternating series, we need to figure out what is our a sub n. So it's everything that doesn't have the alternating part. So we have n plus 2 over n times n plus 1, and that is going to be greater than 0. So it's a positive sequence without the alternating portion. So now we will run the test. So part 1, we need to find the limit as n approaches infinity of n plus 2 over n times n plus 1, which will be the limit as n approaches infinity of n plus 2 over n squared plus n, multiply both by 1 over n squared, the numerator and the denominator. That will give us the limit as n approaches infinity of 1 over n plus 2 over n squared over 1 plus 1 over n, which is 0 over 1, which is 0, which is part of the requirements for the test. So that one works. And now we need to make sure that is a sub n plus 1 less than or equal to a sub n. So going term by term, we will have a2, let's see, will be 4, I'm plugging it in here, okay, so that'd be 4 over 2 times 3, so that would be 4 over 6. A1 is going to be 3 halves. So 4/6 is certainly less than or equal to 3 halves. Let's see if the trend continues. A3 will be 5/12, which is definitely less than or equal to 4 over 6, which was A2. We'll go one more term. A4 will be 6/20, which is less than or equal to 5/12. 5/12 is much closer to 1/2 than 6/20, and that was A3. And so that trend will continue. So we'll say yes. And so step 4, conclusion. The summation as n goes from 1 to infinity of -1 to the n plus 1 times n plus 2 over n times n plus 1 converges by the alternating series test. Cool, cool? All right, excellent. So now we'll do one more of these. I think just one more. Yep, and then we'll go to the root test. So here we go. Step 1. What is our test? We're going to try that ratio test. Step 2, conditions. The summation as n goes from 0 to infinity of n factorial squared over 3n quantity factorial. Remember, 0 factorial is 1. So this is a series with non-zero terms, which is the one condition. All right, step 4, run the test. And so we'll have the limit as n approaches infinity. No need for the absolute value because there's no negative terms. So we will have n plus 1 factorial, that quantity squared, over 3 times n plus 1, that whole quantity factorial. So that's the n plus first term. Now I'm going to multiply it by the reciprocal of the nth term. Just makes it a nicer fraction to deal with. And we will get, so let's see what we have. We're going to fix the n plus 1 factorial. We're going to rewrite that as n plus 1 times n factorial, the whole thing squared, over, and sorry, we need our limit notation. The limit is n approaches infinity, over, we're going to have 3n plus 3, because I see we have a 3n factorial. So I'm going to get this to where it's 3n factorial. So we have a couple, like 3 terms ahead of it. 3n plus 2 factorial, 3n, or not factorial, 3n plus 3 times 3n plus 2 times 3n plus 1, and then times 3n quantity factorial, times 3n factorial over n factorial, the quantity squared. So our 3n factorials divide out to be 1. And then we will get the limit as n approaches infinity of n plus 1, the quantity squared, times n factorial squared, over 3n plus 3 times 3n plus 2 times 3n plus 1 times 1 over n factorial squared. Now our n factorials divide out to be 1. And then we will have the limit as n approaches infinity of n squared plus 2n plus 1 over, so you might see that this is going to go to 0, but just in case your instructor wants it the long way, you'll have, multiplying the first two, we'll get 9n squared. And then we'll have plus 6n plus 9n would be 15n. And then plus 6. Then that in turn will be multiplied by 3n plus 1. So we'll have the limit as n approaches infinity of n squared plus 2n plus 1 over (27) n cubed plus 9n squared plus 45n squared plus 15n plus 18n plus 6, which is the limit as n approaches infinity of n squared plus 2n plus 1 over 27n cubed plus 54n squared plus 33n plus 6. Now, when I multiply, by 1 over n cubed, because n cubed is the highest power of n in the denominator, then I will have the limit as n approaches infinity of 1 over n plus 2 over n squared plus 1 over n cubed over 27 plus 54 over n plus 33 over n squared plus, oh sorry, the 1 would be over n cubed, my bad. It won't change anything. And then plus 6 over n cubed, which is 0. So our conclusion, because 0 is less than 1, so the conclusion would be that the summation as n goes from 1 to infinity, or 0 to infinity, of n factorial squared over 3n factorial converges absolutely by the ratio test. Groovy? All right, now we come to the root test. And so the series summation a sub n converges absolutely when the limit as n approaches infinity of the nth root of a sub n is the absolute value of that, is less than 1. It diverges when the limit as n approaches infinity of the absolute value of the nth root of a sub n is greater than 1, or if it tends to infinity, and it's the root test is again just like the ratio test, it's inconclusive when the limit as n approaches infinity of the absolute value of the nth root of a sub n is equal to 1. Groovy? Okay, so let's check out some examples. Here we go. Step 1, what's our test? It's the root test. And the nice thing about the root test is there's really no conditions. So step 2, conditions, it just has to be a series. So the summation for as n goes from 1 to infinity of 1 over n to the n is a series. And then step 3, run the test. The limit as n approaches infinity of the absolute value of the nth root of 1 over n to the n is equal to the limit as n approaches infinity of 1 over n, which is 0, which is less than 1. So step 4, conclusion. The summation as n goes from 1 to infinity of 1 over n raised to the n converges absolutely by the root test. Groovy? All right, so now we've got this other series in here. So step 1, what's our test? We are trying out the root test. Step 2, conditions. The summation as n goes from 1 to infinity of natural log at n over n, all raised to the n, is a series. And step 3, run the test. So we'll have the limit as n approaches infinity of the absolute value of the nth root of natural log at n over n raised to the n, which will be the limit as n approaches infinity of natural log at n over n. We're starting in at n equal to 1, and so we won't have any negatives, so we can take that absolute value off. So now if we put in infinity, we'd have infinity over infinity, right? And so with direct sub, you get infinity over infinity. So L'Hopital's rule applies. So now we'll need to consider the function that's related to the sequence. And so we'll be looking at f at x is equal to natural log at x over x. And when we evaluate the limit as x approaches infinity of natural log at x over x, that will be equivalent to the limit as x approaches infinity of the derivative with respect to x of natural log at x over x. And we're differentiating numerator and denominator using L'Hopital's rule. And then we'll get the limit as x approaches infinity of 1 over x over 1, which is 0. So the limit as n approaches infinity of natural log at n over n is also 0, which is less than 1. And now our conclusion, step 4. The summation as n goes from 1 to infinity of quantity natural log at n over n raised to the n converges absolutely by the root test. Cool, cool? So let's do a little bit of algebra on this series first. This is equal to the summation as n goes from 1 to infinity of n factorial to the n. And this one we can rewrite as n squared to the n. Cool? And so our first step is to determine which test, and we'll be using our root test. Conditions, you just need to have a series. So the summation as n goes from 1 to infinity of n factorial to the n over n squared to the n is a series. And then now, step 3, we run our test. So we'll have the limit as n approaches infinity of the absolute value of the nth root of n factorial to the n over n squared to the n is equal to the limit as n approaches infinity of, we don't need the absolute value because we have all positive terms, so we'll just get n factorial over n squared. Now, the best way to figure this one out, is to just write out some terms. So the limit as n approaches infinity would be, we'd have an n times n minus 1 times n minus 2 times n minus 3, there'll be lots of n's, times n minus 4 times 3 times 2 times 1, all over. N squared is just n times n. So initially this limit may not go to 0, but as n approaches beyond 3, well, maybe a little further, but as n tends to infinity, this is going to zero out, which is less than 1. And so with our conclusion, step 4, the summation as n goes from 1 to infinity of n factorial to the n over, I'll write the original, n to the n squared, converges absolutely by the root test. Cool? All right. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, hey, hit that subscribe button, maybe share the video, like the video, and I'll see you next time. Bye.